Today we're going to explore one of the most fascinating stories in the history of physics, how a tiny discrepancy in Mercury's orbit led to the first confirmation of Einstein's general relativity. Let's start with what astronomers expected based on Newton's laws of gravitation. According to Newton, every planet should orbit the Sun in a perfect ellipse. Here we see the Sun at one focus of the ellipse, and Mercury following its elliptical path around it. Newton's law of gravitation states that the force equals g times the product of the two masses divided by the distance squared. But in reality, planetary orbits are more complicated than simple ellipses. The ellipse itself slowly rotates over time, a phenomenon called precession. The perihelion, which is the point of closest approach to the Sun, slowly advances around the orbit. This is called perihelion precession. So what causes this precession? There are several known factors in classical mechanics. First, the gravitational pull from other planets, especially the massive Jupiter and nearby Venus, perturbs Mercury's orbit. Second, the Sun is not perfectly spherical. It's slightly oblate, bulging at the equator, which creates a small additional force. Third, there are various tidal effects and other small perturbations. In the mid-1800s, astronomers made extremely careful measurements of Mercury's orbit using precise telescopes and mathematical techniques. They measured that Mercury's perihelion advances by 574 arcseconds per century. Now you might be wondering, what is an arcsecond? It's a unit of angular measurement. 1 degree equals 3,600 arcseconds. So an arcsecond is 1/3600th of a degree. That's an incredibly tiny angle. To put it in perspective, 574 arcseconds is only about 0.16 degrees per century. Astronomers then calculated how much precession should be caused by all the known effects using Newton's laws. Venus, being the closest planet to Mercury, contributes about 277 arcseconds per century. Jupiter, despite being far away, is so massive that it contributes about 153 arcseconds per century. Earth contributes about 90 arcseconds per century. All the other planets and known effects add up to about 11 arcseconds per century. When you add all these up, the total predicted precession is 531 arcseconds per century. But here's the problem. Observations gave 574, but calculations predicted 531. That leaves a discrepancy of 43 arcseconds per century that could not be explained. This tiny difference, less than 8% of the total precession, stubbornly refused to go away, no matter how carefully they checked their observations. Astronomers first wondered if this was just an observational error. Maybe the measurements weren't accurate enough? But no. As telescopes and techniques improved throughout the late 1800s, the measurements were verified again and again. The anomaly was real. So physicists tried everything they could think of to explain this anomaly within Newton's framework. The first hypothesis was that there must be an undiscovered planet orbiting closer to the Sun than Mercury. It was even given a name, Vulcan. Astronomers searched for Vulcan for decades. They looked during solar eclipses, when a small planet near the Sun might be visible. The result: Vulcan was never found. It simply doesn't exist. Another hypothesis was that maybe Newton's gravitational constant g has a slightly different value than we thought. But this didn't work either. Changing g would affect all the other planets, orbits, and their orbits matched Newtonian predictions perfectly. Some physicists propose that maybe gravity doesn't follow an exact inverse square law. Maybe the exponent is slightly different, like 2.00001 instead of exactly 2. The force would be g/mm over r to the power of 2 plus epsilon, where epsilon is some tiny correction. But this also failed. Any modification that fixed Mercury's orbit would break the agreement for other planets. For over 60 years, from the 1850s until 1915, this anomaly remained a complete mystery. It was one of the most famous unsolved problems in physics. Then in November 1915, Albert Einstein published his General Theory of Relativity, which completely revolutionized our understanding of gravity. Einstein's radical idea was that gravity is not a force at all, but rather a curvature of spacetime itself caused by the presence of mass and energy. Massive objects like the Sun warped the fabric of spacetime around them, Planets then follow the straightest possible paths, called geodesics, through this curved spacetime. The Einstein field equations describe how mass and energy curved spacetime, r mu nu minus 1 half rg mu nu equals 8 pi g over c to the fourth times t mu nu. This looks terrifying, but the key insight is simple. The left side describes the curvature of spacetime. The right side describes the distribution of matter and energy. In other words, matter tells spacetime how to curve, and curved spacetime tells matter how to move. Einstein applied his new equations to calculate how Mercury should move in the curved spacetime around the Sun. The calculation is extremely difficult. Einstein worked on it for weeks, solving complex differential equations. The key difference from Newton's theory is that near the Sun, where gravity is strongest, spacetime is significantly more curved. This extra curvature causes Mercury's orbit to precess slightly more than Newton's theory predicts. The formula for the extra precession per orbit is delta phi equals 6 pi gm over c squared a times 1 minus e squared. Let me explain what each term means in this equation. G is Newton's gravitational constant, 6.67 times 10 to the negative 11 in SI units. M is the mass of the Sun, about 2 times 10 to the 30th kilograms. C is the speed of light, 3 times 10 to the 8th meters per second. A is the semi-major axis of Mercury's orbit, about 58 million kilometers. E is the eccentricity of the orbit. Mercury has an eccentricity of about 0.206, making it fairly elliptical. Now let's plug in the numbers and see what we get. The semi-major axis is 5.79 times 10 to the 10th meters. The eccentricity is 0.206. 1 minus e squared equals 0.958. 6 pi gm over c squared equals 2.95 times 10 to the third meters. This is actually the Schwarzschild radius of the Sun. So delta phi equals 2.95 times 10 to the third divided by 5.79 times 10 to the 10th times 0.958. This gives us 5.32 times 10 to the negative 7 radians per orbit. Now we need to convert this to arcseconds per century to compare with observations. 1 radian equals 206,265 arcseconds. So our precession is 0.1038 arcseconds per orbit. Mercury's orbital period is 88 Earth days, so it completes about 415 orbits per century. Multiply 0.1038 by 415, and you get 43.1 arcseconds per century. This was the moment of triumph for Einstein. General Relativity predicts 43.1 arcseconds per century of extra precession. The observed anomaly was 43 arcseconds per century. Perfect agreement! Einstein's theory explained the anomaly exactly, with no adjustable parameters or ad hoc assumptions. When you add the Newtonian prediction of 531 plus the general relativistic correction of 43, you get exactly 574 arcseconds per century, matching the observations perfectly. Einstein later wrote that when he realized his theory correctly predicted Mercury's precession, he was so excited that he had heart palpitations. He said it felt like something actually snapped inside him. After years of struggling with the mathematics, nature had finally revealed one of its deepest secrets. Now you might be wondering, why is this effect so noticeable for Mercury, but not for other planets? There are two key factors that make Mercury special. First, Mercury is the closest planet to the Sun, where the gravitational field and spacetime curvature are strongest. Second, Mercury has a relatively high eccentricity. The more elliptical the orbit, the more pronounced the relativistic effects. Remember our formula. Delta phi is proportional to 1 over a times 1 minus e squared. Smaller a and larger e both increase the effect. Let's compare Mercury to Earth to see how much smaller the effect is for our planet. Earth's semi-major axis is 150 million kilometers, about 2.6 times larger than Mercury's. Earth's eccentricity is only 0.017, making it much more circular. When you calculate Earth's general relativistic precession, you get only about 3.8 arcseconds per century. That's more than 10 times smaller than Mercury's effect, making it much harder to detect against other perturbations. With modern techniques, we've measured Mercury's precession with even greater precision. Using radar ranging and data from spacecraft missions like Messenger, we can now measure Mercury's position to within a few meters. Modern measurements give 42.98 plus or minus 0.04 arcseconds per century. General Relativity predicts 42.98 arcseconds per century. The agreement is now to within 0.1%. This is one of the most precisely confirmed predictions in all of physics. Mercury's precession was just the first of many successful tests of general relativity. In 1919, Arthur Eddington measured the bending of starlight passing near the Sun during a solar eclipse, confirming another prediction of general relativity. The gravitational redshift of light from massive objects has been measured with atomic clocks. GPS satellites must correct for gravitational time dilation. Without general relativity, GPS would accumulate errors of several kilometers per day. In 2015, LIGO directly detected gravitational waves from merging black holes, perhaps the most dramatic confirmation of general relativity. Mercury's anomaly teaches us profound lessons about how science works. First, even tiny discrepancies, less than 8% in this case, can be signals of fundamentally new physics. Second, anomalies that persist despite careful checking are nature's way of telling us our theories are incomplete. Third, truly revolutionary theories don't just make new predictions. They must also explain old puzzles that couldn't be solved before. Perhaps most amazingly, Einstein developed general relativity through pure mathematical reasoning, without specifically trying to explain Mercury's orbit. He followed the mathematics where it led, guided by principles of symmetry and consistency. And then, almost miraculously, when he applied his finished theory to Mercury, it explained the anomaly perfectly. This is the power of mathematics in physics. The right mathematical structure can encode truths about nature that we discover only later. Today, general relativity is not just a theoretical curiosity. It's essential for modern technology. Every GPS device in your phone relies on general relativistic corrections computed millions of times per second. Astronomers use gravitational lensing, where massive galaxies bend light like a lens, to map the distribution of dark matter in the universe. The famous image of the black hole in M87 required massive supercomputer simulations of light rays in the curved spacetime around the black hole. Let me summarize this remarkable scientific detective story. In the 1850s, careful observations revealed a 43 arcsecond per century anomaly in Mercury's orbit. For 60 years, every attempt to explain it within Newton's framework failed. Hypothetical planets, modified constants, nothing worked. In 1915, Einstein's general theory of relativity explained it exactly with no free parameters. Today, we've confirmed the prediction to within 0.1% precision using modern technology. What began as a stubborn anomaly became the first great triumph of general relativity and opened the door to our modern understanding of gravity, spacetime, and the cosmos.